Chapter 12, Sensory Mechanisms, Screencast 1. Now, this set of screencasts on Chapter 12 is focusing entirely on input. So the first screencast will be focusing on general input mechanisms of a nonspecific nature, whereas the remaining screencasts will focus on the special senses. So the first thing we have to look at are overall how this kind of works. So a stimulus, and remember, this is a graded potential. And graded potentials basically diminish in size as they get further from the site of stimulus. So that's one way that the body actually filters out input that we might not need to respond to. A very strong stimulus will result in a very big graded potential, and there's a greater likelihood that that is going to trigger an excitatory postsynaptic potential in the next neuron that it interfaces with on its way to the central nervous system. So once again, some change that causes, or an input that's causing change within or outside the body. And common examples of these are going to be heat or cold, pressure, sound wave, light, and various chemicals. Now, the receptor is a structure that is designed to pick up on that particular stimulus, and there's this concept of energy transduction. So what it's going to do is basically change that sensation into another form. Now, when we look at the general types of receptors that we have in our body, they fall under the following categories. We have mechanoreceptors, thermoreceptors, pain receptors, chemoreceptors, and photoreceptors. So that's really going to be the focus of this particular chapter. Now, mechanoreceptors, they're going to respond to mechanical energy. So examples of those will be pressure, touch, even sound. Okay? Thermoreceptors pretty much speak for themselves. Those are going to be receptors that respond to heat or cold. Pain receptors, those are actually known as free nerve endings, and they will respond to tissue damage, excessive heat, or pressure. Chemoreceptors will be those receptors that are responsive to the presence of specific chemicals. If we look at O2 receptors, CO2 receptors, those are examples, but we'll also kind of talk about those receptors that contribute to taste. Okay? And then last but not least, we have photoreceptors, and they actually are responsive to light. Now here, this is something that I would recommend that you are comfortable with, and I could probably ask this as a matching question in which you have the various types of receptors and the sensation that they are responsible or responsive to. So I would spend some time taking a look at this particular table. We're going to go into a little bit greater depth for all of these. Now, one thing that I want us to keep in mind here is that what our central nervous system interprets are nerve impulses. And so there's a couple of factors here. It's going to be the strength of the stimulus, the area of the brain that this signal is going to, and overall the frequency. Okay, so let's keep in mind a couple of things here. All right, so once again, these impulses move from the receptors to areas of the brain, and this is important. Okay, remember when we talk about a stronger stimuli, that will activate a greater number of receptors specific to that stimulus. The other thing we want to remember here is the impact of the amplitude of a graded potential beyond threshold. Okay, they don't change what action potentials look like, but they will generate more action potentials. So if you have a stimulus that's very much beyond threshold, even by the time it gets to the axon hillock, that says something, okay? Because once again, they degrade as they get further away from the source of the stimulus. So now, if you have a really strong stimulus, you're going to get more action potentials in those sensory neurons. And remember, the overall role of that action potential is to release neurotransmitter. Okay. So once again, all of this is increasing the likelihood that that sensation is moving into higher areas of the central nervous system so that information can be acted upon. Now, one thing that I want us to keep in mind here is this concept of adaptation. Now, not all of our receptors will adapt but there are going to be some situations when there is a chronic stimulus, and kind of going back to a reflex loop, that's going to change the set point of a particular variable or feedback mechanisms. So when we talk about sensory adaptation, that neuron will stop sending impulses or decrease the frequency of firing, even though that stimulus is still present. So this is a way that the central nervous system has to filter and concentrate on those stimuli that are important and ignore things that aren't as important or as much of a danger to homeostasis. Now, the following are receptors that have this phenomena of adapting. So we have light touch, pressure, and smell. Okay, so those are all receptors that will adapt. Now, receptors that do not adapt are going to be pain receptors, joint receptors, and muscle monitoring receptors. So those will not adapt. And once again, their adaptation to not fire based on a particular stimulus could provide danger. So the information that they are providing is critical to maintain homeostasis. Now, if we look at special senses and somatic sensations, these are going to arise from receptors located throughout the body. So we've kind of introduced these already. So temperature, pressure, touch, vibration, pain. And one that you may not be as familiar with is awareness of body position. So knowing where your body or your limbs are with regards to space, especially critical as you're moving. Now, the special senses, those are taste, smell, hearing, balance, and vision. So those are arising from receptors in very special areas. So they're sensitive to those particular sensations, so we refer to them as our special senses. Now, if we look at somatic sensations, so now we're looking at touch, pressure, vibration, pain, and body position. So kind of go back to chapter 11 when we talked about the brain. We have within the brain, in the cerebral cortex, we have this somatosensory area of the parietal lobe. And so this area is responsible for processing the information and sends it to the motor area within the frontal lobe. So here we see a loop, right? So I've got sensation coming in, it moves into the central nervous system, which is the integrator, and then the integration center basically decides on some particular action, and there will be some output based on that sensory information. Now, here, if we look at the types of receptors that we're going to find within the skin. So there's a number of different types. So one of the things that you might be responsible for is I would give you these and you would be responsible for the particular sensation they are responsive to. If I look at unencapsulated dendrites, these are going to detect pain, light pressure, or changes in temperature. So they're not very specific, and that's something you may hear as free nerve endings. Okay. Now, Merkel discs, these are those that are responsive in particular to light touch and pressure. And if you look at where they're located, they're going to be in the higher levels of the dermis. Okay, so just underneath the epidermis. So think about the relationship between location and what these are sensitive to. If I look at Meissner's corpuscles, okay, these are also going to be responsive to the beginning, okay, of pressure, of light touch. So that's what they're responsible for. If I look at Ruffini endings, these respond to ongoing pressure. And then we have Pacinian corpuscles, they're probably my favorite, all right? They're responsible for detecting deep pressure and high frequency vibration. So once again, you want to have an idea of where their general location is. Are they superficial or deep? And what do they actually respond to? Now here, this is this concept known as tonic rate of firing, and this is what results in adaptation. So what I want you to notice here, there's a set point in the firing rate of these particular receptors. So at rest, this is what we're actually seeing. Okay, so let's say that this receptor will fire once every 10 seconds. All right, now let's look at what's happening. There's a degree of stimulus, And look at the increase in the firing rate or generation of action potentials coming from that particular receptor. Now, what we see next here over time, in response to continued stimulation of that receptor by the touch here, notice what happens. That resets. Okay? Now, a really good example, and this isn't going to be specific to everyone, but kind of imagine, okay, some of you out there, okay, may wear your hair up in a ponytail. Okay? Not a really tight ponytail, just get your hair up out of the way. And you feel it in the very beginning. Okay? Then, though, because that ponytail is still in that position, your body gets used to it. And you now have a chronic rate of stimulus. And this is not something that's going to be critical to disturbing homeostasis or life-threatening. So now you reset the firing rate of that particular receptor. And so now it slows down and it becomes similar to what it was at rest. Then you probably feel it again when you let your hair down. Okay? So that's a really good example of adaptation to a chronic stimulus. Now, mechanoreceptors, these are those that are specific to limb position, muscle length, and tension. Another name for them are proprioceptors, and we're going to find them in a couple of different places. In joints, they detect joint position. In skeletal muscle, they are known as muscle spindles, and they are really important because they monitor muscle length and will respond if they experience too much stretch. Also, we have tendons. They are known as Golgi tendon organs specifically, and they detect the force in that particular joint. So these are very protective in nature, and these do not adapt. So here, let's take a look at the muscle spindle. And what the muscle spindle does, basically, as you stretch, because of its position, it stretches also, and it sends signals. Now, if it stretches too much, there's the potential for injury to that muscle. So the stimulus or the output will be to contract that muscle, which is shortening it. So now you basically have released the stimulus by shortening the muscle when it was in danger of stretching too much and creating injury. Now, if we look at a tendon receptor, those are specific to force. So what will happen if you stimulate those to a greater degree, that muscle will actually relax. Kind of imagine you're helping a friend move furniture. You're going up some stairs with something really, really heavy. And then all of a sudden, okay, those muscles that are holding up the furniture just fail. Because what happened was the force produced by trying to prevent that piece of furniture from falling or holding it up was potentially creating damage to that particular joint, and you see a sudden failure. That muscle just relaxes automatically. So that's another good example of how these receptors work. And keep in mind, they're protective in nature. Now, thermoreceptors, they kind of speak for themselves. These are receptors that are at the surface of the skin, and they are giving information about our external environment. Now, these surface thermoreceptors adapt relatively quickly. Okay. Now, there's some in some areas, like the thoracic and abdominal organs, those are responsible for monitoring core temperature. Now, those within the core do not adapt quickly, and that's important because one of the things that the body is going to do is regulate body temperature, and it's going to focus on the core. Those peripheral areas, so fingers, toes, tips of your ears, things like that, the body is not caring as much about those areas with regards to the core. So one thing that might happen, especially in the cold, is blood vessels will vasoconstrict to those particular areas, and also those are areas that are more susceptible to frostbite or injury from cold or heat. Now, if we have pain receptors, so these are quite often known as free nerve endings, and these will respond to a number of different types of injuries overall. So it could be too much pressure, light, chemical sensations or burns, any of those things. Now, we have two different types of pain. We have fast pain, and this occurs very quickly, and this is actually protective in nature. All right. So the example that I like to use, if you touch something too hot, you pull away. If you step on something really sharp, you pull your foot away. So these are examples of fast-acting pain. Now, slow pain, on the other hand, this is pain that occurs much more slowly. And it's coming from muscles or internal organs. So some examples might actually be the pain that a person experiences from cancer, or more specifically, you may be familiar with that pain related to someone experiencing a heart attack. We refer to that as referred pain. And so if we look at the area of sensation that someone might feel when they're experiencing a heart attack, you'll hear about radiating pain into down the left arm, up into the neck, up into the jaw. So it's not pain at the chest where the heart is, it's referred pain based on the receptors in that particular area. Now, another thing that's important when we talk about pain receptors, they do not adapt at all. And once again, that's important because they overall are protective in nature.